Hello friends, IBM is here with an episode of Learning Physics, and today I would like to take you to another unit which will be physical quantities and units. Do not forget we are actually dealing with solved past paper questions. This is specifically AS past paper questions. These are questions quoted from paper 2 of AS Physics. Remember, this is Physics 9702, Advanced Level Cambridge. So today I want us to discuss the simpler questions of AS Physics, and in this unit or in this part of physical quantities, it is actually physical quantities and units, or physical quantities and base units, or physical quantities and measurements. And in this unit we expect to discuss questions about base units or base quantities and units. You expect to see questions about estimates, questions about errors and uncertainties. Expect to see questions about precision and accuracy. Expect to see questions about scalars and vectors and so many more. So without wasting any time, I would like to take you to the document of solved past paper questions and we try to solve them. So without wasting time, so here is the document, Master Kit A-Level Physics, Physics 9702, revision questions for paper 2, and this is a try edition of 2022. That is my name. That's where I get my initials, IBM. My contact details are there. In case you have a question, you can write to me an email. I will answer it. And this is the content, the table of contents. So we are actually dealing with the first part, which is physical quantities, units, and measurements. So we are somewhere there. So straight away, let's go to page 2 and start answering these questions. So make estimates of the mass in grams of a new pencil. One important thing I want to note here, or I want to mention here, is that estimates can be written to at least two significant figures, actually at most. At most, two significant figures. You can't write an estimate to so many significant figures. It would mean it is not an estimate, but a measured quantity. So for a pencil, a new pencil, I think a new pencil has mass between 1 gram to around 20 grams. That is a new pencil. Most pencils have mass around 10 grams, so I will just quote 10. Any value between 1 gram and 20 gram is the mass of a new pencil, depending on the manufacturer, but the mass is between 1 gram and 20 grams. Then the wavelength of ultraviolet radiation. Here you don't just guess, you have a guiding tool. Menera's mother is visiting Uncle Xavier's garden. These are the electromagnetic waves. Here we have the visible spectrum, which ranges between this side infrared, we have red, and the other side we have violet. Red is 7 times 10 power negative 7 meters, and violet is 4 times 10 power negative 7 meters. Now we want ultraviolet, which is on the other side of violet. That means the wavelength must be decreasing as move the other side. So the wavelength should be less than 4 times 10 power negative 7. Therefore, I can choose a value between 7 times 10 power negative 7 meters and maybe 10 power negative 8 meters, because the value must be less than 4 times 10 power negative 7. For instance, I can say, okay, it is maybe 1 times 10 power negative 8 in meters. So that is a range in that, a value in that range. So that is the wavelength of ultraviolet. Then the period T of the oscillations of a mass M suspended from a spring is given by that expression, where K is the spring constant of the spring. The manufacturer of the spring constant states that it has a spring constant. The manufacturer of a spring states that it has a spring constant of 25 newtons per meter, plus or minus 8%. A mass of 200 times 10 power negative 3 kilograms plus or minus 4 times 10 power negative 3 is suspended from the end of the spring and then made to oscillate. Calculate the period T of the oscillations. So we just substitute in that expression. The period T is going to be equal to 2 pi square root of 200 times 10 power negative 3 divided by 25. So this time I think I have a calculator here. Let me try to find a calculator. This time I'll have a calculator here. Okay, so I have my calculator here. Have my calculator, but has failed. Okay, it is here. So my calculator, I'll just enter this into my calculator because one student told me, teacher, I have a problem with using my calculator. So this time I decided to bring one. So I will have 2 pi square root of I'll open the brackets. So that is 200. Or I'll just say 200 times 10 power negative 3 is the same as 0.2. Then divide by, this is 25. So that is, I think that is all. So this gives me my answer. You can see the answer on my screen. So this is actually going to be 0.56. 0.56, as you can see it here. So two significant figures is 0.56. So the period here is 0.56. Okay. Determine the value of T with its absolute uncertainty to an appropriate number of significant figures. So we are going to determine the value of T. Now note that from the previous part, one of them, the spring constant was given in percentage, its uncertainty is in percentage, and yet the mass is in absolute. So we can make them uniform, we can use percentages. Since T is equal to 2 pi square root of m over T, over K, so we shall take percentages. When we are taking percentages or when we are dealing with the fraction uncertainties, we don't take the constant 2 pi into consideration. So the percentage uncertainty in T will be equal to, there is a root, so that is a half. The power is a half because of the square root, into the percentage uncertainty in M plus the percentage uncertainty in K. So the percentage uncertainty in T is going to be a half into the percentage uncertainty in M. We shall get the absolute was 4 times 10 power negative 3 divided by the true value, which is 200 times 10 power negative 3, then times 100 to make it percentage, plus percentage in K has been given as 8%. So I can bring my calculator and we verify. So I have 4 times 10 power negative 3, that is 0.004. So I'll to simplify life, I'll say 0.004, of course, times 100, divide by 200 times 10 power negative 3 is 0.2. So plus 8%. Then I divide this by 2 because of this half here. So divide by 2, that is 5%. Therefore, we are saying the percentage uncertainty is 5%, but that's not what we want. We want absolute. To find absolute uncertainty, we convert percentage into absolute. So absolute uncertainty is going to be 5 over 100 times the true value of t, or the value of t that we have calculated above, was 0.56. When I press my calculator, so 5 divided by 100 times 0.56, and that is so we get 0.028, and we write this to one significant figure. One significant figure there will be 0.03, so this is approximately 0.03, and therefore these are two decimal places, so we shall write t also two decimal places. So t will be 0.56 plus or minus 0.03. So this is 0.56 plus or minus 0.03. Okay, so that is the value there. Distinguish between a scalar, a vector, and a scalar. Of course, we know that a scalar has only magnitude. Scalar has only magnitude. Vector has both. Has both magnitude and direction. Okay. The electric field strength E at a distance x from an isolated point charge Q is given by that expression. Although electric field strength was removed from AS, we shall still answer it here. We know that electric field strength from A level is the force acting on a unit positive charge. So use the definition of electric field strength to show that E has SI base units as that. So electric field strength E is force acting on a unit positive charge. We know that the base units of force, are kilograms per meter squared, or mass times acceleration, which is kilogram per meter squared. And we also know that the units for charge is IT, so charge is ampere times seconds because it is IT. So it means the units of electric field strength will be equal to kilogram meters per second squared divided by ampere seconds, and we now divide. So when we divide, the units of electric field strength will be kilogram meters. When I divide s power negative 2 by s, it becomes s power negative 3. Then I have 1 over a, which will be a power negative 1. As simple as that. Use the units for E given in B to determine the SI base units of B. SI base units of B. So to find the base units of B, we begin by making B the subject from this expression here. From that expression, you'll notice that B making it the subject will be Q divided by x squared times E. I've made B the subject. So Q is ampere seconds. X, what is X? X is a distance, the base units are meters. So the base units of X will be meters, the rest we have them. Which means therefore the units of B will be ampere seconds for charge divided by meters squared times E, which is kilogram meters per second cubed per ampere. So we simplify this. Ampere divided by per ampere, it becomes ampere squared. So this is ampere squared. S divided by s power negative 3 becomes s power negative 4. We are saying s power 1 divided by s power negative 3. We subtract the powers. So this will be s power 1 minus negative 3, which becomes power 4. Then we have m squared times m, that is m cubed, but it is in the denominator. So when it goes up, we have 1 over m cubed, which is the same as m power negative 3. Then we have 1 over kilogram, which is per kilogram. So this can be written as per kilogram. The order doesn't matter. Per kilogram per meters cubed, ampere squared, and oh, by the way, this is s power 4. So those are the base units of B. Those would be the base units of B. The ampere, meter, and the second are SI base units. State two other SI base units. The ampere, meter, and second are SI base units. The base units are supposed to be 7 because they are 7 base quantities. So apart from those ones, we have the kilogram, or you can write kg. We have Kelvin, that is for temperature. Kelvin, that is capital K. Of course, we have others such as the mole, which is the unit for amount of substance. We have others such as we have the candela. This time I'm suffering with this. The eraser is not very close. So we have the candela, that is the unit of luminous intensity. Those are the base units. The question wanted base units, not base quantity, so you must be very careful with that. The average drift speed v of an electron moving through a metal conductor is given by that expression. E is the charge on an electron, F is the force acting on the electron, mu is a constant. Determine the SI base units of mu. So first of all, I will make mu the subject. So mathematically, mu is going to be equal to E times V divided by F. Let's list the units. V is speed, and speed is in meters per second. E is charge, and charge is ampere seconds because it is IT. Then F is force, and force is mass, which is in kilograms, times acceleration, which is in meters per second squared. So we now combine the units. The units of mu will therefore be ampere seconds multiplied by meters per second divided by kilogram meters per second squared. So we simplify this. Ampere is alone, so I will maintain it. S times s power you have s times s power negative 1 over s power negative 2. This is the same as 1 over s squared power negative 2 because these ones cancel. Or you add the powers for multiplication and you subtract the powers for division. That is s power 1 plus negative 1. Then because of division, you subtract again minus negative 2, which is equal to s power 2. So that is s squared. Then we have m and m, those ones have cancelled out, m and m. Then kilogram is in the denominator, 1 over kilogram is per kilogram. So this is per kilogram. So I can write this as ampere second squared per kilogram as the SI base units there. The speed v of a sound wave through a gas of pressure P and density ρ is given by that equation. So this is the equation we need, where K is a constant and K has no units. An experiment is performed to determine the value of K. The data from the experiment are shown in the figure. So we have a table here of quantities, values with the uncertainties. Use data from the figure to calculate K. So we are going to make K the subject there. When I make K the subject, I square both sides. So I have that V squared is equal to KP over rho, which means that making K the subject, K is going to be equal to V squared times rho divided by P. That is K making K the subject. So we are substituting now. V, all these ones are in their SI units, so I will not convert. So V squared is going to be 3.3 times 10 power 2, and this should be squared. Then times density, which is 1.29, divided by the pressure, which is 9.9 times 10 power 4. So I'll press my calculator. So I have 3.3 times 10 power 2, that is 3.3 times 100, squared, then times 1.29 divided by 9.9, where is exponent 4. So this is giving me a value as 1.419. That is the value I'm getting there, 1.419. It is 1.419. Use your answer in B Roman 1 and data from the figure to determine the value of K with its absolute uncertainty to an appropriate number of significant figures. Absolute uncertainties are going to always be written to one significant figure. So we are going to find, we have already a value of K, we shall just find uncertainty. Note that there is a square, there is multiplication, there is division. So we either add the fraction uncertainties or we add the percentage uncertainties. So we shall simply say percentage uncertainty in K is equal to, because of the power on V, this will be twice percentage uncertainty in V plus percentage uncertainty in rho plus percentage uncertainty in P. You must have studied this with your teacher. So this is going to be 2 times percentage in V. From the table, percentage in V is 3 plus 4, percentage in rho is 4 plus percentage in P is 2. And I think that is 6 plus 6, which is 12%. That is percentage uncertainty, but we are interested in absolute. So to change from percentage to absolute is easy. Absolute in K is going to be 12 over 100 times the value of K, which is 1.419. So I'm going to multiply the value of K, which I got there, times 12 divided by 100. And this is giving me 0.17, which is approximately 0.2 to one significant figure, and that is one decimal place. So it means I'll write the value of K to one decimal place since the uncertainty is one decimal place, 0.2. So this will be 1.4 as my value there. So I think that is easy. You can look at it. Next, the diameter D of a cylinder is measured as 0.0125 plus or minus 1.6%. Calculate the absolute uncertainty in this measurement. Absolute, just convert percentage to absolute. So absolute uncertainty in D is going to be the value of the percentage, which is 1.6, converted to out of 100. Then times the value of D, which is 0.0125. So I'll check this on my calculator. 1.6 divided by 100 times 0.0125, and that is giving me 2.0 times 10 power negative 4. You can see it there yourselves. 2.0 times 10 power negative 4, or 2 times 10 power negative 4. Then the cylinder in A stands on a horizontal surface. The pressure P exerted on the surface by the cylinder is given by that expression. The measured weight W of the cylinder is 0.38 newtons plus or minus 2.8%. Calculate the pressure P. So pressure P, we shall just substitute. Pressure P is equal to 4 times W. W is the weight, which is 0.38, divided by pi times D squared, and D was 0.0125, and this is squared. So I'll just press my calculator and check. So I have 4 times 0.38 divided by, I will open the bracket, and I will say pi times 0.0125, and this is squared. So this is giving me a value which is 3096.51. I'll just write 3096.51 of 0.52. So this is going to be approximately 3100. If I round off to two significant figures, this will add a 1 there. So it becomes 3100 Newton per meter squared. Then determine the absolute uncertainty in the value of rho. Absolute uncertainty. So here we have a percentage for W, and we also had a percentage for D. So I'll just use percentages. Because pressure is equal to 4W divided by pi D squared. Since I'm seeing division and the power, I ignore the constants in that expression. So percentage uncertainty in P must be equal to percentage uncertainty in W plus twice percentage uncertainty in D. So I'm substituting. Percentage uncertainty in P will be equal to, for W, that is 2.8%, plus for D, which is 2 times 1.6. And I think that is 3.2 plus 2.8, that is 6.0%. But the question wants absolute, so absolute uncertainty in P is going to be percentage 6.0 over 100 times the value of P, which we found as 3096.52, which is going to be, so I'll just multiply this times 6 divided by 100. This is giving me 185. It is 185.8. 185.8 to one significant figure. If you want, it can be to one significant figure, it can be 200. But since they do not want us to write any value, so, and we just want absolute, we can say this is approximately 190. Okay, define resistance. Of course, resistance from V equals to IR. R is V over I. So resistance is going to be defined as potential difference over current. Potential difference per unit current, or potential difference over current. That is resistance. A potential difference of 0.6 volts is applied across a resistor of resistance 4 gigaohms. Calculate the current in picoamperes in the resistor. So we know that giga is 10 power 9, and pico, I think pico is 10 power negative 12. 10 power negative 12 pico. So we want to calculate the current. Of course, we know that the current is going to be equal to V over over R. So V is 0.60 and R is 4.0 times 10 power 9 to change it to ohms rather than giga. And if I check my calculator, 0.6 divided by 4 exponent 9. So this is 1.5 times 10 power negative 10 in amperes. But we want the answer in pico, so we are going to divide by 10 power negative 12. So I is going to be 1.5 times 10 power negative 10 divided by 10 power negative 12. So this answer is going to be divided by 10 power negative 12, and that is 150. So the current there is 150. The energy E transferred when charge Q moves through an electric component is given by that equation. V is the potential difference across the component. Use the equation to determine the SI base units of potential difference. So we make V the subject. Remember, E is energy transferred and energy is work done. So we can start with E. The base units of E is work done, which is equal to force times distance. Remember, force is kilogram meters per second squared and D is meters. That means the units of E are going to be kilogram meters per second squared times meters, which will be kilogram meters squared per second squared. And then Q is charge. The units of charge is IT, I times T. Charge is equal to current times time, so ampere times seconds. So that is ampere seconds. So we are making V the subject. V is going to be equal to E divided by Q. So the units of V will therefore be kilogram meters squared per second squared divided by ampere seconds. And when you divide, this is going to be kilogram. Meters squared is still standing alone. S power negative 2 divided by S. We subtract the powers. So it becomes S power negative 2 minus 1, which becomes S power negative 3. Then 1 over ampere, it becomes per ampere. So the answer here will be kilogram meters squared per ampere per second cubed. Okay, the length, mass, and temperature are all SI base quantities. State two other SI base quantities. The SI base quantities, remember, there are 7. Length, mass, and temperature have been given, so we are remaining with the time. Those are now 4. We have electric current. Those are 5. We have amount of substance. Those are 6. We also have luminous intensity. Luminous intensity. So luminous intensity, I think there is no U here. So time is measured in seconds, current in amperes, amount of substance in moles, luminous intensity in candela, length in meters, mass in kilograms, temperature in Kelvin. Those are the base quantities. The acceleration of free fall g may be determined from an oscillating pendulum using this equation. L is the length of the pendulum and t is the period. In an experiment, the measured values for an oscillating pendulum are given here. We have L and we have t. Calculate the acceleration of free fall of g. So we just substitute. So g is going to be 4 pi squared times the value of L, which is 1.50, it is in meters, divided by t squared, which is 2.48, and that is squared. So check with our calculator. So from our calculator, we need 4 pi squared, then times 1.5 divided by 2.48, and this is squared. So we are getting the value of g as 9.628. Okay, so g is, since they didn't specify the number of significant figures, I'll write it as 9.63. Determine the percentage uncertainty in g. Since they have given us percentages for L and T, we shall just consider percentages directly. So since the formula has 4 pi squared L over T squared, the percentage uncertainty in G will be equal to percentage uncertainty in L, we ignore the constants, plus the power, this will be twice percentage uncertainty in T. So we are getting the sum, that is 2% plus 2 times 3, which gives us 8%. So this is 8%. Use your answer in B Roman 1 and B Roman 2 to determine the absolute uncertainty of the calculated value of G. So we want absolute, we just convert percentage to absolute. So percentage uncertainty in G is going to be equal to 8 divided by 100 times the value of G that we obtained earlier on was 9.628. So I'll just say that value which we have times 8 divided by 100. And this is giving us 0.77. So since we don't need to use it for writing, I can write 0.77 or 0.8, because remember, the absolute uncertainty is good enough to one significant figure. So you can write 0.77 or 0.8 or 0.77. However, if the next part wanted us to write G with the uncertainty, we would write G as 9.6 plus or minus 0.8, not 0.77 in this case. The appropriate number would be 0.8, 9.6 plus or minus 0.8, not 0.77. Although 0.77 would be marked at this stage, if the next stage was asking to write G with its absolute uncertainty, you would round off absolute uncertainty to one significant figure. Use an expression for work done in terms of force to show that the SI base units of energy are kilogram meters squared per second squared. So work done, I'll use W for work done, that is force times displacement. Force times displacement in the direction of the force. Work done is force times displacement in the direction of the force. We know the units of force. Force is mass times acceleration, which is kilogram meters per second squared. And the displacement is meters. So it means the units of work will have units as kilogram meters per second squared times meters, which gives us kilogram meters squared per second squared as required. The energy E stored in an electric component is given by that expression, where Q is charge. Q is charge, C is a constant, E is energy stored. Use the equation and the information in A to determine the SI base units of C. So we just make C the subject. If I make C the subject, you will notice that C is going to be, of course, here you cross multiply and divide. So C is going to be equal to Q squared divided by twice E. And Q is charge. The units of Q are ampere seconds. Then C is what we want to find. We have found the energy units of energy above. So the units of C will therefore be, Q squared, which is ampere squared times second squared. Because Q is squared, I'm squaring A and S. Then we ignore the 2 in the units, so we just write the units of energy, which is kilogram meters squared per second squared, and then we simplify. A is standing alone, so it is S squared. S power 2 divided by S power negative 2. S power 2 over S power negative 2, that is S power 4. So that is S power 4, we subtract the powers. That is S power 2 minus negative 2, which is S power 4. Then we have 1 over m squared, that is m power negative 2, and 1 over kilogram, that is kilogram power negative 1. So the units here will be ampere squared, S power 4 per kilogram, and per meter squared. Measurements of a constant current in a wire are taken using an analog ammeter. For these measurements, describe one possible cause of a random error. Note that a random error makes values to scatter around the true value. What causes the random error? There are 2 possible or common causes of random error or sources of random error. Number 1, if we read a scale from different angles, it is almost impossible to read a scale from the same angle. This makes values to scatter. So number 1, reading the scale from different angles. Reading the scale from different angles. Sometimes we are taking a reading between 2 divisions, and the reading you are to take is somewhere in between the 2 divisions. So when you are taking the reading in between 2 divisions, you do what we call interpolation. So sometimes you may wrongly interpolate between scale readings or divisions. So wrongly interpolating, between scale divisions or scale readings. Then a systematic error. Of course, a systematic error many times comes with the instrument. And there are two common systematic errors which may come with the instrument. Number one, we expect a zero error. That is, the instrument gives a reading even when a measurement is not being taken. Number two, there could be a wrongly calibrated scale. Wrongly calibrated scale. Sometimes when you use two analog ammeters for the same measurement, you notice that they give slightly different values. This could be as a result of one of them, which we cannot choose which one of them maybe is wrongly calibrated. So that's why they could give different values. The dragger force Fd, so Fd is force acting on a car moving with a speed v along a straight horizontal road, is given by this expression. K is a constant and A is the cross-sectional area. Determine the SI base units of K. So we begin with the force Fd. Fd is force, which force has units kilogram meters per second squared. Then V is speed. V is speed, which speed has units meters per second. A is area or cross-sectional area, which has units meters squared. So we want to find the units of K. We make K the subject from that expression. K is going to be equal to Fd divided by V squared times A. So it means the units of K, we are just going to substitute Fd, which is kilogram meters per second squared, divided by meters per second, but this one is squared, times meters squared. So we simplify. In the numerator, you can have kilogram meters per second squared. In the denominator, when you square, you have meters squared times meters squared, which is meters power 4, and s power negative 2. So you notice that s power negative 2 cancels out. So you remain with the kilogram. Meters divided by meters power 4, we subtract the powers. Meters over meters power 4 is meters power 1 minus 4, which is meters power 3. So this is m power negative 3. So the units are kilogram per meters cubed. Perhaps K is density. The value of K in SI base units for the car in B is 0.24. The cross-sectional area A is 5.1. The car is traveling with a constant speed along a straight road, and the output power of the engine is 4.8 times 10 power 4 watts. Assume that the output power of the engine is equal to the rate at which the force Fd is doing work against the car. Determine the speed of the car. Okay, so we know from from work, energy, and power that power can also be given as force times velocity. So this time the force is Fd, because they said the output power is equal to the rate at which the dragger force is doing work. So the force is Fd, for Fd is the one doing work, but Fd, so this would be Fd times V, but Fd is given above by an equation which is V squared AK. So this is V squared times A times K, again times V. So it becomes V cubed. Therefore, power, which is 4.8 times 10 power 4, is equal to V, this is going to be V cubed times A, which is A is 5.1 times K, which is 0.2. 0.24. So we make V the subject, so V cubed is going to be equal to 4.8 times 10 power 4 divided by 5.1 times 0.24, and we shall find the cube root. So what is V? So I'll just pull out my calculator. So we have 4.8 exponent 4 divided by, or maybe I will use brackets, 4.8 exponent 4 divided by, open another bracket, 5.1 times 0.24, close that bracket. And that is V cubed. So I find the cube root. Do I have cube root on this calculator? So the cube root is here. And that is giving me 33. So V is 33.97, which is approximately 34. State one similarity and one difference between distance and displacement. Of course, we know that similarity, distance and displacement, they both have magnitude. So both have magnitude, they have size. Remember, magnitude is just a number and a unit. Both have magnitude, but then difference. Difference, we know that distance is a scalar, displacement is a vector. Distance is a scalar, or you could say does not have direction, or does not consider direction. And then displacement is a vector. Or you can say it has what? It has direction. It can also be speed and velocity. Velocity both have magnitude, that is a similarity. But speed is a scalar, that is, it has no direction, but velocity is a vector, it has direction. Okay. A student takes several measurements of the same quantity. This set of measurements has high precision but low accuracy. Describe what is meant by high precision. What does high precision imply? Remember, precision is how close the measured values are to each other. That means how the magnitude of the range between the values. So high precision means the range is very small, or the values are very close to each other. So the measurements, high precision means the measurements have a small range. The measurements have a small range. In other words, they are close to each other. So the measurements are very close to each other, or the measurements have a very small range. Then low accuracy, it means the average of these measurements First of all, it is not the true value and is not close to the true value. The average of the measurements is not close to the true value. So that is the difference between precision and accuracy. Define the moment of a force, although this is in another unit. We shall see moment in force, density, and pressure. The moment of a force is the product of force times perpendicular distance. That is force times perpendicular distance. Force times perpendicular distance of the line of action of force to the pivot. In other words, is force times perpendicular distance to the pivot. That is moment of a force. Perpendicular distance of line of action of force to the pivot. That is moment. We shall see that in force, density, and pressure. Determine the SI base units of moment. So since moment is force times perpendicular distance, the units for force, that is kilogram meters per second squared. And the unit for distance, that is meters. So the units for moment will therefore be kilogram meters per second squared times meters, which gives us kilogram meters squared per second squared. A uniform rigged rod of length 2.4 meters is shown in the figure. So the length is 2.4. The rod has weight 5.2 newtons and is of wood of density 790 kilograms per meters cubed. Capture the cross-sectional area A in millimeters squared. So since they have given us weight, we know that weight is equal to m times g. But we don't have the mass directly. We know mass is density times volume. So this would be density times volume times g. We don't have the volume. We have density. We don't have the volume. We have the length and cross-sectional area. Volume is cross-sectional area times length. So this would be density. Where there is volume, I put cross-sectional area times length, then times g. So now it becomes easy for me to find the cross-sectional area. I'm just substituting the weight. Weight is 5.2, equaling to the density, which is 790, times the cross-sectional area. The length is 2.4. G is 9.81. So I just divide. Cross-sectional area is going to be equal to 5.2 divided by 790 times 2.4 times 9.81. So I'll just bring my calculator. So I have 5.2 divided by, I'll open the brackets, 790 times 2.4 times 9.81. So this is giving me 2.8. So that is 2.8 times 10 power negative 4 meters squared. Note that that is cross-sectional area in meters squared, but we want the answer in millimeters squared. You and me note that 1 meter is the same as 1000 millimeters. 1 meter squared is the same as 1000 millimeters, but the whole of it is squared. Which means this is going to be 1 times 10 power 6 millimeters squared. So to convert from meters squared to millimeters squared, I'm going to divide by 10 power 6. I'm going to multiply by 10 power 6 because this side I have in meters squared, I want to convert into millimeters squared. So I'll multiply by 10 power 6. So this is going to be 2.8 times 10 power 4 negative times 10 power 6, which gives us 2.8 times 10 power 2 millimeters squared. So you need to know this simple conversion of quantities. An electromagnetic wave has wavelength 85 micrometers. State the wavelength in meters. We have a prefix which is micro. To remove a prefix, we multiply by its value. So that gives us 85 times 10 power negative 6. And if you want to check this on the calculator, 85 times 10, or you just set 85 exponent negative 6. It is the same as 8.5 times 10 power negative 5. 8.5 times 10 power negative 5. Calculate the frequency in terahertz of the wave. Frequency. From the general wave equation, we know that the frequency is going to be V over lambda or C over lambda. Since this is electromagnetic, the speed is the speed of light. So this is 3.0 times 10 power 8 divided by the wavelength, which is 8.5 times 10 power 5. I mean power negative 5. From my calculator, we have 3.0 exponent 8 divided by the answer. This is giving me 3.5 times 53 times 10 power 12. 3.53 times 10 power 12. That is the frequency in hertz. To change it to tera, remember tera is 10 power 12. So to bring in a prefix, we divide by its value. So the frequency is going to be 3.53 times 10 power 12 divided by 10 power 12. So that is going to be 5.35 or approximately, 3.53 or approximately 3.5, because this one cancels with that. Say the name of the region of the electromagnetic spectrum that contains this wave. So you don't just guess, you have to look at, I think it is easier to see the region by looking at the wavelength. Rumenera's mother is visiting Uncle Xavier's garden. Here we have the visible spectrum, which is from 7 times 10 power negative 7 for red and 4 times 10 power negative 7 for violet. The wavelength we have is 8 0.5 times 10 power negative 5. You notice that it is on the left of the visible spectrum. However, when you add here negative 2, when you add positive 2, you get negative 3. That is, okay, when you add 7 times 10 power negative 7 plus on the power I add 2, it becomes power negative 5. That is automatically infrared. So it means this is going to be infrared. Because on red, if I add positive 2 on the power of 10, I get negative 5. That means I get the negative, the next wave there, the next region, which is power negative 5. When I add another 2, I get negative 3, which will be microwaves. When I add another 2, I get negative 1, which is radio waves. On the other side, you go on subtracting 2. So this is going to be infrared. The current I in a coil of wire produces a magnetic field. The energy E stored in the magnetic field is given by that expression. Where L is a constant, the manufacturer of the coil states that the value of L in SI base units is that value there. The current I in the coil is measured as that value 0.5 plus or minus 0.02. The value of L and I are used to calculate E. Determine the percentage uncertainty in the value of E. Okay, so we want the percentage uncertainty in the value of E. So percentage uncertainty in E, because of the square on I multiplication, we shall add the percentage uncertainties. So percentage uncertainty in E is going to be twice percentage uncertainty in I plus percentage uncertainty in L. So we can substitute. Of course, percentage in I, we multiply the fraction by 100. So this is going to be 2 times percentage in I, which is 0.02, divided by 0.50 times 100 to make it percentage, plus percentage in L is 5%. So this is going to be, I think 0.02 is 4%, over 0.5 is 4%. So 2 times 0.02 times 100 divided by 0.5, that is 8. 8 plus 5, that is 13. So this is 13%. You can verify. So I hope you have verified. Determine the SI base units of stress. Of course, by definition, we know that stress is force over area, over cross-sectional area. The base units of force, that is kilogram meters per second squared, and for area, that is meters squared. So we just substitute. So the base units of stress will be kilogram meters per second squared divided by meters squared. And when you divide m by m squared, this gives us kilogram per meter per second squared. A beam PQ is clamped so that the beam is horizontal. A mass M, 500 grams, is hung from the end Q and the beam bends slightly as illustrated here. The length L of the beam of the clamp R to the end Q is 60 centimeters. The width B of the beam is 30 millimeters and the thickness D of the beam is 5 millimeters. The material of the beam has Young modulus E. The mass M is made to oscillate vertically. The time period T of the oscillations is 0.58 seconds. The period T is given by that expression. Determine E in gigapascals. So the easiest way is to make E the subject first so that we substitute directly. From this expression, I'm squaring both sides. So this is T squared. So we have that T squared is equal to 4 pi squared into 4 m L cubed divided by E B D cubed. So I'm only going to remove E and bring it the other side. So E is going to be equal to 4 times 4 4 times 4, I think that is going to be 16. So that is 16 pi squared times m times L cubed divided by, in the denominator I have T squared times B times D cubed. So let's see which values to substitute in. So this gives us 16 pi squared and m, the mass is 500 grams, I think, which is 0.5. L, the length was 60 centimeters. 60 divided by 100 to change it to meters, that is 0.6, but is raised to power 3. So 0.6 cubed divided by, the period T was 0.58, but it is squared, times B. B was 30 millimeters. 30 millimeters is 30 over 1000, which is 0.03. So that is 0.03 times D. D is 5 millimeters. 5 divided by 1000, that is 0.005. 0.005, but this is raised to power 3. I'm converting them here so that it is easy to make to press the calculator for anyone, whether PCB or not. Let's check now. So we have 16 pi squared times 0.5 times 0.6 cubed, 0.6 cubed. So that's what you get, divided by, in the denominator you have 0.58 squared times 0.03 times 0.005 cubed. So this is giving us 1.0 1.35 times 10 power 10. So 1.35 times 10 power 10. And this is in Pascals. That is in Pascals. We now want the answer in Giga. Giga is 10 power 9. So to bring a prefix, we divide by its value. So this is going to be 1.35 times 10 power 10 divided by 10 power 9, which is going to be 1.35 times 10 power 1, which is 13.5. So this is 13.5. In other words, I'm dividing the answer by exponent 9, which is 13.5 gigapascals. You can also press your calculator and verify. The quantities used to determine E should be measured with accuracy and with precision. Explain the difference between accuracy and precision. Note that accuracy determines how close the measured values will be, or the average of the measured values will be to the true value, and precision will determine how close these values are to each other. That is, they will determine the range between the values. So accuracy, this is determined by it is going to be determined by the closeness of the values to the true value. Determined by closeness of the measurements. Closeness of the measurements to the true value. And the precision will be determined by the range of the measurements. In other words, how close the values are to each other. So that is the difference. For accuracy, it is going to be determined by the closeness of the measurements to the true value, or the closeness of the average of the measurements to the true value. And precision is going to be determined by how close the values are to each other. In a particular experiment, the quantities L and T are measured with the same percentage uncertainty. State the value, state and explain which of these two quantities contributes more to the uncertainty in the value of E. When you go back to the expression, you see that L is raised to power 3 and T is raised to power 2, but they have the same percentage uncertainty. So, and remember, we multiply the power by the percentage uncertainty. For L, it will be 3 times the percentage uncertainty, and for T, it will be 2 times the percentage uncertainty. So you notice that L is going to contribute more because it is cubed. So we say L is cubed. L is cubed. So contributes 3 times the percentage uncertainty. And we see that T is squared. So it contributes 2 times the percentage uncertainty. Hence, L contributes more. Hence, L contributes more because its value is 3 times the percentage uncertainty. Its contribution is 3 times the percentage uncertainty. State 2 SI base units other than kilogram, meter, and second. So we have seen the base units, they are 7, the 3 have been given. So kilogram for mass, meter for length, second for time. So we have temperature, that is Kelvin. We have amount of substance, that is mole. We have current, that is ampere. We have luminous intensity, that is the candela. So those are the other SI base units. The SI base units of resistivity. Resistivity from electricity, you know resistance is equal to rho L over A, or you know that resistivity is equal to R A over L. We also know that V is equal to I times R. So it means R is going to be V over I. So resistivity is going to be, where there is R, I'm putting V over I times A divided by L. That is VA over IL. Again, we know that V is equal to power over I. From electricity, power is IV. And we also know that power is work done over time. So power is work done over time. So this will be work done over time times I. And we also know that work done can be force times distance. So this will be force times distance over T times I. That is still, we are still finding V. Now it is easy to write the units of V. Force is going to be kilogram meters per second squared. Distance is meters. We are using the units of work done. Divide by T, time is in seconds, and I is in amperes. So it means the units of V are going to be kilogram, meters and meters, that is meters squared, S power negative 2 divided by S, that will be S power negative 3. Then 1 over A is going to be A power negative 1. That is for V. So we now substitute because I is ampere, A is meters squared, L is in meters. So it becomes easy. So the units of resistivity will be V, which is kilogram meters squared S power negative 3 per ampere, divide by, I'm substituting this expression, I is in amperes, L is in meters, then there's cross-sectional area which is meters squared. So we simplify. When we simplify this, we remain with the kilogram. Meters squared times meters squared over meters, it becomes meters cubed. Meters squared times meters squared, that is meters power 4, divided by meters, that is meters cubed. Then times S power negative 3. Then ampere power negative 1 divided by ampere, it becomes ampere power negative 2. Therefore, the base units will be kilogram, meters cubed, S power negative 3 per ampere squared. You can also verify that. A wire of cross-sectional area 1.5, length 2.5 meters, resistance 0.03 ohms. Calculate the resistivity of the material of the wire in nano ohm meters. Nano. So we have seen resistivity is R times A divided by L. I substitute. R is 0.03. Cross-sectional area is 1.5. I change it to meters squared. So this will be times 10 power negative 6, because 1 meter is 1000 millimeters. 1 meter squared is 1000 millimeters, but is squared. That is 1 times 10 power 6. So when I move from millimeters to be times 10 power negative 6. In other words, we divide by 10 power negative 6. Divide by the length L, which is 2.5. Answer. So we have 0.03 times 1.5 exponent negative 6 divided by 2.5. So that is 1.8 times 10 power, it is 10 power negative 8. But this is in ohm meters. So we divide this by 10 power negative 9 to bring in the nano. And when you divide by 10 power negative 9, so divide by exponent negative 9, that is 18. So resistivity is 18 nano ohm meters. State what is meant by precision. We have said precision is how close the measured values are to each other. It is determined by the range in the measurement. So I will say precision, it's determined by the range in the measurements. It is determined by the range in the measurements or in the readings, that is how close measurements are to each other. How close measurements are to each other, that is precision. Explain why the precision of the value of resistivity is improved by using a micrometer screw gauge rather than a meter ruler. Why not a meter ruler but a micrometer screw gauge? We know that a meter ruler measures, the smallest division is 1 millimeter. Therefore, a meter ruler measures to plus or minus 1 millimeter. But a micrometer screw gauge, the smallest reading is 0.01 millimeters. So it measures to plus or minus 0.01 millimeters. So we expect that there is a less random error in the micrometer than the meter ruler. So the meter ruler or the meter rule measures up to plus or minus 1 millimeter, measures to plus or minus 1 millimeter, and the micrometer measures to plus or minus 0.01 in millimeters. So there is a less random error with the micrometer. So there is less random error with a micrometer. There is less random error with a micrometer. Two forces with magnitudes 5 newtons and 12 newtons act from the same point on an object. Calculate the magnitude of the resultant force R for the forces acting in opposite direction. So there are two forces acting at a point but in opposite direction. So one is 12 newtons another one is 5 newtons. So we just subtract. So I think here the resultant is going to simply be 7.0. Then at right angles, let's say 12 newtons is acting upwards and 5 newtons is acting in that direction. So the resultant is here, which can be found by Pythagoras theorem. This is say 12 newtons, this is 5 newtons, so this is the resultant. Because this is 90 degrees, so the resultant is going to be the square root of 5 squared plus 12 squared. I think that is 5 squared plus 12 squared, square root of the answer, that is 13. The object X rests on a smooth horizontal surface. Two horizontal forces act on X as shown in the figure. A force of 55 newtons is applied to the right. A force of 18 newtons is applied at an angle of 115 degrees to the direction of 55. Use the resolution of forces or scale diagram to show that the magnitude of the resultant force is 65. I'll begin by using resolution. I'll use resolution here because resolution to me is easy on a computer. So I'll use resolution here. Then I'll maybe try to do scale. So for resolution, we have here 55 newtons, and we have here 18 newtons. So I'll draw a vertical line. I'll change the color to, I'll draw a vertical line here. So this angle is going to be 90 degrees. Remember the whole angle was 115, so we have 115 minus 90, which makes this angle 25, or this angle is 65, which is 180 minus 115, that is 65. So you can choose which angle to use for your resolving. So when I resolve 18 in the horizontal, it will point in that side. So resolving horizontally, that will be 18 cos 65. That is cos 65. Resolving 18 vertically, it will point downwards and it will be 18 sine 65. If I use 65, if I use 25 in the horizontal, it will be 18 sine 25. In the vertical, it will be 18 cos 25. So it depends on which angle you have used. So F in the horizontal is simply going to be 18 cos 65 plus 55. And F in the vertical is simply 18 sine 65. So since they are at 90 degrees in the x and in the vertical, we just find the resultant from the square root. So the resultant force, I'm calling it FR, will be the square root of 18 sine 65, but this is squared, plus 18 cos 65 plus 55, and this is also squared. That is Pythagoras theorem. When you have two vectors at 90 degrees, use Pythagoras theorem. One is f in the x, the other one is f in the y. So they are at 90 degrees, we use Pythagoras theorem. So I will press my calculator. I'll say square root of open brackets. I'll open another bracket. 18 sine 65 squared plus, open another bracket, 18 cos 65 plus 55, close that bracket, squared, and then I close the outer bracket. So that is giving me 64 It is 64.697 or 0.7, which is approximately 65. Approximately 65. You can verify the resolving yourselves. So for those who are not good at resolving, I want to take an opportunity to show you some the scale diagram. I'll use this space here for the scale diagram. So I failed to install a protractor and a ruler on my computer, so I'll just try to use the hard copies of these rulers. They called hard copies. So I'll choose a scale. Let's say I hope this space is big. So using a scale diagram, you had two choices: resolving or scale. So for a scale, I would say 1 centimeter will represent 1 newton. No, not 1, 10 newtons. 1 centimeter will represent 10 newtons, so it means 18 newtons. I will measure. Let me use the other side for the scale. So 1 centimeter will represent 10 newtons. For 18 newtons, I will measure 18 over 10, which is 1.8 centimeters. For 55 newtons, I will measure 5.5 centimeters on my question paper. So of course these vectors have been joined head to tail, which means if I draw a sketch, the resultant will be from one end to another end. So the resultant will just be there. That will be the resultant. So I just want to draw this to scale. So to begin with, I'm going to draw a horizontal line here. I don't have enough space, so I have to rub off this line. I want to use this space for the scale diagram. So I'm going to draw a horizontal line. And on this horizontal line, I will measure 5 centimeters to represent 5.5. So I hope my ruler works for me very well. So I'm drawing a horizontal line. I may not be very accurate because I'm drawing on a computer. So I'll say starting from this point here, does it make 5 centimeters, 5.5? So I'm saying starting from that line, 5.5 is around here. So this is pointing that direction, that is 55 newtons. On that line, I've measured 5 centimeters. Then I'll put a protractor to measure 115 degrees. So I'm putting a protractor. It is not easy to put a protractor on a computer, but I'm trying. So when I get a protractor for the computer, I'll be enjoying. So I'm measuring 155. I've put my protractor on my computer. So 115 degrees from the left, from the right, 0, 10, 20, 90, 110. So 115 is somewhere here. Okay. So 115, I have measured 115 and I'm drawing another line. So that is 115. This angle here, I've measured approximately 115, and this is in this direction. But on this line of which is making an angle of 115, I must measure only 1.8 centimeters. So I'm measuring off 1.8 centimeters using my ruler. I know 1.8 was very small, but I didn't have enough space. And 1.8 is around here. So 1.8 is around here. So I'm going to join where 1.8 stops, where 1.5 stops to find the resultant. So I have tried my level best to draw this to scale. So this is going to be my resultant force R. This is 18 newtons. This is 55. So what remains is I measure the distance from this point to that point. And I'm measuring that distance. Remember me, I may not be very accurate because I'm using rulers and protractor on a computer. So I am getting this as 6 point, you can't imagine it is exactly 6.5. So I'm getting R as 6.5 in centimeters times the scale, which is 10. That gives me 65 newtons as the result. So you just measure the length represented by R and you multiply by the scale. That will be the resultant as required. Okay. Then determine the angle between the resultant force and the 55 Newton force. So we want the angle between the resultant force and the 55 Newton force. Maybe to draw a sketch here. 55 is in the horizontal, that is 55 newtons. But when you resolve, I noticed that Fy was pointing downwards. So Fy was pointing downwards, which was, oh, by the way, in the horizontal there was 55 plus 18 cos 65. In the vertical there was 18 sine 65, and therefore the resultant is there. We want the angle between the resultant and 55. So this is going to be, vertical is 18 sine 65 in the vertical, downwards. So opposite adjacent, that is tan. Therefore it means theta is going to be the tan inverse of the opposite, which is 18 sine 65 over the adjacent, which is 55 plus 18 cos 65. So let's see this. Tan inverse of 18 sine 65 divided by 55 plus 18 cos 65, then close the outer bracket. And this is giving me is it 12? Let me repeat. Tan inverse, open the first bracket, or let me first solve the brackets for simplicity. So I have 18 sine 65 divided by, open brackets, 55 plus 18 cos 65, close that bracket, That's what you get. So we get the tan inverse of the answer, and it is 14.6 or approximately 15 degrees. If you have drawn to scale, you don't need to calculate that. You just come to your diagram and put your protractor there. The angle we want is this one here. So just put the protractor. Just put the protractor. So I'm putting there my protractor, and shockingly I have 14. Actually, it is 15. So theta is actually 15 using a protractor. So you can also verify that. A third force of 80 Newtons is now applied to X in the opposite direction to the resultant. Remember, the resultant is 65 Newtons. Now a third force is in the opposite direction to the resultant, so our new resultant force is going to be the difference between those two. So resultant force is going to be the difference between the two, that is 80 minus 65, which I think is 15 Newtons. Then find the acceleration. We know that resultant force is equal to mass times acceleration. So the acceleration is going to be 15 divided by the mass, which is 2.7. From your calculator, 15 divided by 2.7, and that is 5.5. So that is 5.5 Newtons. One end of a wire is connected to a fixed point. A load is attached to the other end so that the wire hangs vertically. The diameter d of the wire and the load F are measured, and they are given here. D is 0.4, F is 2.5. For the measurements of the diameter of the wire, state the name of a suitable instrument. For the measurements of the diameter, look at the diameter, 2 decimal places in millimeters. I think that is a micrometer screw gauge. It can also be a digital caliper or digital calipers. Digital calipers. How random errors may be reduced when using the instrument. Of course, when we use a micrometer screw gauge or digital calipers around the instrument, we just take several, if this is the wire, we take several measurements around different points and obtain the average. So take several readings along the wire and obtain the average. And obtain the average. So if we want to take to obtain a more reduce random errors, we take several readings around the material, and then we obtain the average. The stress sigma in the wire is calculated using this expression. Show that the value of sigma or stress is 1.99. So just substitute. Sigma is going to be equal to 4 times F, where F is, they gave us F here as 225. So that is 25.0 divided by pi. D, they gave us D as 0.4, but it was in millimeters. We have to change it to meters. So it will be times 0.4 times 10 power -3, and this is squared. So let's check with our calculator. So we have open brackets 4 times 25, close that bracket, divide by, open another bracket. Even if I don't open that bracket, I'll say divide by pi into brackets 0.4 exponent -3, and this should be squared. So we are seeing that this is giving us 1989, which is 1.99 times 10 power 1, 2, 3, 4, 5, 6, 7, 8. So it is 1.99 times 10 power 8 as required. Then determine the percentage uncertainty in sigma. So they gave us absolute uncertainties. So percentage uncertainty, we shall just multiply the fractional by 100. So percentage uncertainty in sigma is equal to, we ignore the constants. So it will be percentage in F, which will be delta F over F times 100 plus percentage in D, delta D over D times 100, but D is squared. So there should be a 2 somewhere here. So there's a 2 there. And this will be multiplied by 100. So this will be equal to, for F is 0.5 over 25.0 plus 2 times D, which D is 0.02 over 0.4. And this should be multiplied by 100 to get percentage. So let's check. So we open the brackets, 0.5 divide by 25, then plus, open another bracket, 0.4, because 2 times 0.02, that is 0.04, divide by 0.4, close the brackets, then times 100, that is 12%. So that is 12. You can check. So unfortunately, the question just wanted a percentage uncertainty. If it included defining absolute, we would just change from absolute to percentage directly. Okay. All bodies radiate energy. The power radiated by a body is given by that expression. P is equal to Ka T power 4, where T is the thermodynamic temperature of the body, A is the surface area, and K is a constant. Determine the SI base units of K. SI base units of K. Of course, making K the subject, K is equal to power over AT power 4. A is area, the base units of A are going to be meters squared. T is thermodynamic temperature, the base units are K power 4. And P is power. Power is equal to the work done over time, and work done is force times distance over time. So it means the base units of power are going to be force, which is kilogram meters per second squared times meters, divided by seconds, which would be kilogram meters squared per second power -3, because S goes up. So it means the base units of K would therefore be power, which is kilogram meters squared per second power -3, divided by A, which is meters squared, times T power 4, which is K power 4. And you notice that M squared has cancelled, so I remain with the kilogram S power -3 and K and capital K power -4 as the base units of K. Okay, Sketch the variation with the t squared of p. When you look at the expression, you see that actually t power 4 is directly proportional to p, which means that t squared is going to be directly proportional to the square root of p. That means p increases more rapidly than as t increases. If t increases by 1, or I can just factor this out. If t increases by 1, it means p is increasing many times than t as t increases, because the other one has a power. So it means p increases more rapidly as t increases. That means the gradient of this graph must be increasing. Of course, when t is 0, p is 0. Obviously, the graph starts from the origin. But as t increases, p increases more rapidly, meaning that the graph becomes steeper. So the curve will be going upwards like that. Let me draw a better curve. Like that. P increases more rapidly than t. The speed v of a transverse wave of on a uniform string is given by that expression, where T is the tension in the string, L is the length, and m is its mass. An experiment is performed to determine the speed v of the wave. The measurements are shown here. You can see the measurements are given as percentages. State an appropriate instrument to measure the length L. We look at the size. 126 centimeters is the same as 12.6 meters. We divide by 100. I think that can be measured using a meter ruler or a tape measure. A meter ruler or a tape measure. Or simply tape. Use the data in the figure to calculate the speed v. They've given us the expression for v as the square root. V is the square root of t L over m. So I substitute. All quantity, or L is the one which is not in SI units. The mass is 5.1 times 10 power negative 3 in kilograms. So this would be the square root of 1.8 for T times 126, that is 12.6 in meters, divided by 5.1 times 10 power negative 3. So let's check this with the calculator. So the mass, this is going to be square root of, open brackets, 1.8 times 12.6 divided by, so let me first close this bracket, divide by, open another bracket, 5.1 exponent negative 3. And this is giving us, is that true? (1.8) times 12.6 divided by 5.1 exponent negative 3. Root of the answer, I'm getting 60. Am I converting wrongly? 128 centimeters divided by 100, 126. Oh, sorry, this is 1.2. Yeah, 1.26, not 12, it is 1.26. So let me press again, square root 1.8 times 1.26 divided by 5.1 times, 5.1 exponent negative 3. So this gives us 21.09, or approximately 21.1. Use your answer in part B Roman 1 and data in the figure to determine the value of V with its absolute uncertainty to an appropriate number of significant figures. So we want to determine the value of V with its absolute uncertainty. So since V is equal to that, the percentage uncertainty in V, because there is a square root, it will be power, it is a half, because square root is power half, into brackets percentage in T plus percentage in L plus percentage in M. This will be a half into percentage in T is 5, percentage in L is 1, percentage in M is 2, which I think that is 8 over 2, which is 4%. So the percentage uncertainty in V is 4%, then we want the absolute. Absolute uncertainty is going to be 4 over 100 times 21.1 or 21.09, which will give us, I'll just multiply that answer times 4 divided by 100. That is 0.84. To one significant figure, it is 0.8. So this is 0.8. So V should be written to one decimal place. So that is 21.1. Make estimates. Make estimates. Mass in kilograms of a wooden meter rule. Of course, we use meter rulers almost every day. And the mass of a meter ruler, I think the mass of a meter ruler is approximately, a normal meter ruler is around 120, 115. But it depends on which ruler you are using. So we can say the mass is between 50 to 200 grams. 50 grams to 200 grams, or 50 to 200 times 10 power negative 3. But me, I will take the normal mass of in the laboratory is 110 grams, which is 0.11. But since I want this to a small number of significant figures, this is going to be 0.1 kilograms. 0.1 kilograms, that is 100 grams. That is the mass of a meter ruler. Then the volume in centimeters cubed of a cricket ball. A cricket ball, you can try to estimate its radius or its diameter, and then you try to find the volume. If you consider it being spherical, volume is going to be equal to 4 over 3 pi r squared. You can look at your ruler and you imagine a cricket ball. If you say the radius is say 3 centimeters, so I'll say this is going to be 4 over 3 pi times 3 squared. And from my calculator, this will be 4 pi divided by 3 times 3 squared. That is around 37, but that is, no, this is cubed, not squared. Volume is cubed. So I'll multiply this answer again times 3. and that is approximately 111 or 110. So this is approximately 110. But a cricket ball has volume between 50 centimeters cubed to 300 centimeters cubed. So me, I will take 100. So you choose a value in that range. A metal wire of length L has a circular cross-sectional area of a circular cross-section of diameter D. As shown in the figure, the volume V of the wire is given by that expression. The diameter and mass M are measured to determine the density of the metal of the wire. The measured values are shown here. D is measured as 0.38 plus or minus 0.01. L is 25.0 plus or minus 0.1. M is 0.225 plus or minus 0.001. Calculate the density of the metal with its absolute uncertainty. Give your answer to an appropriate number of significant figures. Density. So to find density, to begin with, density is mass over volume. We don't have the volume, we have the mass. We know that volume is equal to cross-sectional area, which is pi r squared times the length L. Since we don't have r but we have d, we shall replace r with d. So this will be pi, where there is r I put d over 2, and this is squared times L. So it means the volume is pi d squared L over 4. So it means density, I'm substituting for the volume, which is going to be mass over volume, which volume is pi d squared L over 4, so the 4 goes up. And in the denominator we have pi d squared L. Now we substitute. So this is going to be 4 times the mass. The mass is 0.225 times, we change it to kilograms, 10 power negative 3. Divide by pi, diameter, 0.38 times 10 power negative 3, and this is squared, times the length L. L is 25 times 10 power negative 2 because it is in centimeters. So we can check this with our calculator. So this is going to be, open brackets, 4 times 0.225 exponent negative 3, divide by, open brackets, divide by pi into brackets, did I press pi, 0.38 exponent negative 3, but this is squared. I can first divide by that, and again divide by the last part, which is 25 exponent negative 2. So this is giving me 7,935.7. 7,935.7, and this is in kilograms per meters cubed as the density. So we have finished to find the density. We now want the uncertainty. So the reason as to why I had to bring in D is to make finding uncertainty easy. So fractional uncertainty in density is going to be equal to fractional uncertainty in the mass plus twice fractional uncertainty in D plus fractional uncertainty in L. So the absolute in density is going to be for M. M is 0.001 over 0.225 plus 2 times D, 0.01 over 0.38 times, plus, for L, 0.1 over 25.0. And I will multiply this by the value of rho, that is times 7935.7. So I have open brackets 0.001 divided by 0.225 plus open bracket 0.02 over 0.38 plus open bracket 0.1 divided by 25. So that is the answer times the value of density, which is 7935.7. So this is giving me a 484.7. And to one significant figure, this is 500. Once non-zero digit, that is 500. So this is going to be 500, ending with two zeros. It means I will modify my value of density to be a whole number ending with two zeros. So that will be 7,900. So those are the 5 marks. Describe the effects, one in each case, of systematic errors and random errors when using a micrometer screw gauge to take readings for the diameter of a wire. If there is a systematic error, what does it do? Remember, we know that a systematic error will make the values either to be above or below the true value by a constant amount. It makes the average to deviate either above or to be below. So a systematic error, it means the reading is larger or smaller, but not at the same time. Smaller than the true reading or smaller than the true value by a constant amount. Then random errors, we know random errors makes readings to scatter. So here, scatter in readings about the true value. Scatter in readings about the true value. That is for the random errors. Distinguish between precision and accuracy when measuring the diameter of a wire. We know accuracy, the measurements of the diameter, or accuracy will be looking at how close the measured diameter is to the true value of diameter, and precision will actually be looking at the size of the smallest division on the measuring instrument, and to be looking at how small the measured values, how small the range between measured values is, and this depends on the smallest division. So to begin with, accuracy will be concerned with how close the diameter value is to the true value. How close is the diameter value measured? How close the diameter value is to the true diameter value. How close the measured diameter, how close the measured diameter value is to the true value. How close the measured diameter value is to the true value, and precision will be concerning with the size of the smallest division the size of the smallest division on the measuring instrument. And for the micrometer screw gauge mentioned above, it is 0.01 millimeters for the micrometer. So the size of the smallest division on the measuring instrument and is 0.01 millimeters for the micrometer. Okay, define the density. Define density. We know that density is mass divided by volume. The mass per unit volume, that is density. The mass m of a metal sphere is given by that expression, where ρ is density of the metal and d is the diameter of the sphere. Data for the density is given here. It is in percentage. The answer is in percentage. The values are in SI units. Calculate the diameter d. So we make it the subject from this expression. Making it the subject, you see that d is going to be equal to the cube root of 6 times the mass over pi times rho. So this is power a third, cube root. When we substitute, this is 6 times the mass. The mass is 7.5 divided by pi times the density is 8100. And this is under cube root or power a third. So let's press our calculator and see. So 6 times 7.5 divided by pi times 8100. Then we find the cube root. Then define the cube root of the answer. I said the cube root of the answer said 6 times 7.5 divided by pi times 8100. Then we find the cube root of the answer. So this is 0.1209. Okay, so the diameter is 0.1209. Use your answer in Roman 1 and the data in the figure to determine the value of d with its absolute uncertainty to an appropriate number. This is very important, an appropriate number of significant figures. So since we have a clear formula for d and there is a power of a third, it will be multiplied by the percentage uncertainties. So percentage in d is going to be a third into percentage in m plus percentage in rho. So this will be a third into percentage in m is 4, percentage in rho is 5. So that is 5 plus 4, which gives us 3%. Then we find the absolute. The absolute uncertainty in d is going to be simply 3 over 100 times the value of d, which we calculated as 0.1209. So that answer times 3 divided by 100. So this is going to be 3.6 or 0.0036, which is approximately 0.004 to one significant figure, and these are 3 decimal places. So our answer should also be 3 decimal places. So this is 0.004 and this is 0.121, 3 decimal places. define pressure. So we know that pressure is the force acting normally per unit area. Force acting normally. That is, the force must be at 90 degrees to the area. The force acting normally per unit area. That is pressure. Show that the SI base units of pressure are that. So since pressure is force over area, and we know the units of force, we know the units of area, so the units of pressure, since it is just 1 mark, would be kilogram meters per second squared divided by meters squared, which gives us kilogram meters over meters squared becomes per meter seconds power -2. Gas flows through the narrow end nozzle of a pipe. Under certain conditions, the mass m of the gas that flows through the nozzle is in a short time t is given by that. So mass over time is given by that. K is a constant with no units. C is a quantity that depends on the nozzle size. Rho is density. P is pressure. Determine the base units of C. So we make C the subject. And I will see that C is equal to m over T divided by K square root of rho times P. So m over T, that is mass per unit time, has units as mass is kilograms over seconds, that is per second. Then K has no units. They said K has no units. Rho is density. Units of density, that is kilogram per meters cubed. Then P is pressure, whose units we have got as kilogram per meter per second squared. So we now find the units of C. The units of C, we have m over T, which is kilogram per second, divided by K, no units, I will ignore it, divided by the square root of kilogram per meter cubed times kilogram per meter per second squared, which is kilogram per second divided by, this is square root of kilogram squared, m power -3 times m power -1, that is m power -4, s power -2, which is going to be kilogram per second divided by square root now. That is kilogram. Square root of m power -4 is m power -2. Square root of s power -2 is s power -1. So s power -1 cancels out, kilogram cancels out. So you remain with 1 over m power -2, and 1 over m power -2 is the same as m power 2. Use the definition of power to show that the SI base units of power are kilogram meters squared per second. So by definition, power is defined as work done over time. But work done can be defined as force times distance in the direction of the force over time. So it means that the base units of work are going to be kilogram for force, meters per second squared, times meters. That is kilogram meters squared per second squared. So the base units of power will therefore be kilogram meters squared per second squared divided by seconds, which simplifies to kilogram meters squared per second power -3. That is for use an expression for electrical power to determine the SI base units of potential difference. Electrical power. So we know that for electrical power, power is equal to I times V, that is electrical power. We want for V is equal to power over I. We know the base units of power in part A. We know the base units of power in part A, and we know that I is amperes, and the power is kilogram meters squared per second power -3. So it means the base units of V will be power, which is kilogram meters squared per second cubed divided by ampere, which gives us kilogram meters squared per second cubed per ampere as the base units of potential difference. Use the definition of work done to show that the SI base units of energy is that. So we know that work done, work is force times displacement, or distance in the direction of the force. So we know the base units of force are kilogram meters per second squared, and the base units of the displacement are meters. So the base units of work, which will be the same as those of energy, will be kilogram meters per second squared times meters, which is kilogram meters squared per second squared. These are the same as those of energy. Define potential difference. Of course, potential difference is the energy transferred from electrical. We know that V is equal to work done per unit charge, energy transferred per unit charge. So that is energy transferred from electrical to other forms. To be specific, to thermal. Per unit charge. Determine the SI base units of resistance. So we can use expressions for power. We know that electric power P is equal to I squared times R. We want resistance, so resistance is power over I squared. And we know that the base units of I squared will be actually ampere squared. We also know that power is work done over time. So the base units and power work done is force times distance over time. So the base units of power will be for force, which is kilogram meters per second squared times meters divided by seconds, which simplifies to kilogram meters squared per second cubed. That is power. So the base units of R, which is resistance, will be kilogram meters squared per second cubed for power divided by I squared, which is ampere squared. And this simplifies to kilogram meters squared per second cubed, then per ampere squared. Okay. The distance between the Sun and Earth is 1.5 times 10 power 11 meters. State this distance in giga meters. Giga is 10 power 9. To bring a prefix, we divide by its value. So 1.5 times 10 power 11 divided by the value of the prefix, 10 power 9. 1.5 exponent 11 divided by 1 exponent 9. So that is 150. So that is 150. The distance from the center of the Earth to a satellite above the equator is 42.3 megameters. The radius of the Earth is 6380 kilometers. A microwave signal sent from a point on the Earth directly below the satellite. Calculate the time taken for the microwave signal to travel to the satellite and back. That means it travels the distance twice. Which distance does it travel twice? If this is the Earth, whose radius is known as 6380, and the satellite is somewhere there in space, then they have said the distance from the satellite to the center of the Earth is 42.3. So it means the distance from the surface of the Earth to the satellite, we subtract these two values. And remember, the signal goes to the satellite and back, so we shall multiply that distance by 2. We shall multiply that distance by 2. Okay, so let's simplify this. So the distance is going to be 2 times 42.3. Mega is 10 power 6, minus, I'll also change this from kilo to mega. Remember, kilo is 10 power 3. To change it to mega, to be 10 power 3 divided by 10 power 6. So that would be 6.38 times 10 power 6. So this is times 10 power 6. That is the distance. Then time is going to be distance over speed. And speed is the speed of light. So the time is going to be 2 times 42.3 minus 6.38 times 10 power 6 divided by the speed, which is the speed of light, 3.0 times 10 power 8. So we can check this. So we have 2 into brackets 42.3 minus 6.38. That is times exponent 6. Sorry. Open, okay, 2 times open brackets 42.3 minus 6.38 close the brackets exponent 6. What's wrong with that? 42.3 minus 6.38 times 2 times 1 exponent 6 divided by 3 exponent 8. So this is 0.24. The time is 0.24. The speed v of a sound wave through a gas of density ρ and pressure P is given by that expression, where C is a constant. Show that C has no units. P is pressure. Pressure is force over area. The units of pressure will be for force, which is kilogram meters per second squared, divided by area, which is meters squared. So for pressure, it is kilogram meters divided by meters squared, that is per meter, then S power negative 2. Then the other one is density. Rho is kilogram per meters cubed. V is speed, which is meters per second. So we make C the subject. Square both sides. This side squared, the other side squared. The square root goes off. So you see that C is going to be V squared times rho over P. The units are going to be V squared, which is meters squared, S power negative 2. We square meters per second. Then times density, kilograms per meters cubed. divide by pressure. The pressure is kilogram per meter per second squared. So I'm going to simplify this. So I have kilogram meters power negative 3 times meters power 2. You get meters power negative 1. S power negative 2. Divide by kilogram per meter per second squared. So we now cross out term by term. Kilogram by kilogram, per meter by per meter, per second by per second. We conclude that C has no units. Underline all the scalar quantities in the list below. Scalar, we have energy, we have power, the rest are vectors. Remember, there are 6 vectors: acceleration, displacement, velocity, momentum, force, stroke, weight, and moment. The rest are scalars. A boat travels across a river in which the water is moving at that speed, 1.8 meters per second. The velocity vectors of the boat and the river water are shown here. In still water, the speed is 3 meters per second. The boat is directed at an angle of 60 degrees to the river bank. Draw a vector triangle or a scale diagram to show the resultant velocity of the boat. So I will just draw a vector triangle. I'll transfer 1.8 onto this vector so that it is head to tail, and the resultant is going to be somewhere here. So that is my vector triangle. Because you will notice that this angle 60 is the same as this, because those are Z angles, or I think they are alternating angles. If I draw the water velocity as a horizontal line, if this is 60, the other is also 60. So you can use a scale diagram, but I will use the vector triangle. If I use the vector triangle, so here I can use the cosine rule. So this is opposite. This one is 1.8 meters per second. This is 3 meters per second. So using the cosine rule, I have that r squared is going to be 1.8 squared plus 3.0 squared minus 2 times 1.8 times 3.0 cos of 60, which is the angle between the vectors after joining them head to tail. The angle after joining the vectors head to tail. So I will just press my calculator here. So I have 1.8 squared plus 3 squared minus 2 times 1.8 times 3 cos of 60. So that is the answer. I find the square root. And the square root is, the resultant is 2.6. You can use a scale diagram, although it is hard to draw the diagram I will choose a scale. So these are simple values. I will simply say that let 1 centimeter represent 1 meter per second. So for 18 meters per second, I will measure 1.8. For 1.8 meters per second, I will measure 1.8 centimeters. 3 meters per second, I will measure 3 centimeters. So let me try to sketch this, although I don't have enough space. I will sketch it here. Let me sketch it just here. So this is another method, which is drawing to scale. I've been looking for space. I will sketch it here. I use the smallest scale so that I have enough space. You can use a larger scale. So I'll draw a horizontal line And this horizontal line I will measure off only 3 centimeters. So this is 3 centimeters. No, it's not like that. 3 centimeters is not like that. I will draw a horizontal line and I will put a starting mark somewhere here. Then I'll measure an angle of 60 degrees from the horizontal. So I put on my protractor, and I think 60 is around here. So I'm measuring 60 degrees. So that line is for 60 degrees. This is 60 degrees. On this line which I've drawn, I'll measure only 3 centimeters to locate the magnitude of the velocity. So 3 centimeters is somewhere here. So this is 3 centimeters. So that is 3 meters per second. Stops there, the magnitude. Then I can draw another horizontal line, or I measure 60 degrees again there, but I'll just draw a horizontal line here. So I draw a horizontal line there. I know that this angle is also 60 degrees, but on this line I'll measure only 1.8. So I'm measuring off 1.8. 1.8, I think 1.8 is around here. So my resultant, I'll change the color for the resultant. My resultant is here, and it is pointing upwards. So that is my resultant. So how do I find the magnitude of the resultant? I just measure the length. So I'm measuring the length of representing the resultant. That is 0, and it is exactly 2.6. So R is 2.6 centimeters. Since 1 centimeter is 1 meter per second, so R is 2.6 meters per second by scale. You may not be accurate to get exactly 2.6, but at least it is approximately that. You could have used a scale which multiplies 1.8 by 2 to get 3.6. That is, you could say 1 centimeter to represent 0.5 meters per second. A beam is clamped to one end of an object. I think this is the last question for this video, for part 1. A beam is clamped at one end, and an object X is attached to the other end of the beam, as shown here. The time period T of the oscillations is given by that expression. M is mass, that is kilograms, L is length, that is meters, E is Young modulus of the material, and K is a constant. So that the SI base units of the Young modulus are kilogram per meter per second squared. Of course, you and me know that Young modulus is stress over strain. Stress over strain. And we know that stress is force over area. And you also know that strain is extension over original length. So we substitute. Young modulus is going to be force times original length over area times extension. So now we find the units. The base units, force, that is kilogram meters per second squared. Original length, that is meters. Area, that is meters squared. Extension, that is meters. So M cancels. So this gives us kilogram, M over M squared, that is per meter, and per second squared. It's the same as pressure. Then determine the SI base units of K. So we make K the subject from this expression here. I'll just divide both sides. So K is equal to T over the square root. I don't need to remove the square root. Square root of ml cubed divided by E. So I know T is period, base units are seconds. L is length, base units meters. M is mass, base unit kilograms. And we have those for E. So it means the base units of K are going to be seconds divided by the square root of kilogram, then times meters cubed divided by kilogram per meter per second squared. Of course, kilogram has cancelled. This is seconds divided by m power 3 over m. This is square root of m power 3 over m power 1. That is m power 4. Then 1 over s power negative 2, it becomes s power 2. When I find the square root, I have s over square root of m power 4 is m power 2, square root of s squared is s. So s has cancelled. So I have 1 over m squared. And 1 over m squared is m power negative 2. So this is m power negative 2. Okay. Data in SI units of the oscillations of X are shown in the table. They are in percentages. You can see them. Uncertainties are in percentages. The values are in SI units. Calculate E and its actual uncertainty. So we just substitute find E. So E is equal to, remember I made E the subject, or I can make E the subject here. To make E the subject here, I have to square. So I have T squared equals to K squared into M L cubed over E. Then I cross multiply to find E. So E is going to be K squared ML cubed over T squared. So E is equal to K squared ML cubed over T squared. I'm substituting. So K is 1.48 times 10 power 5, and this is squared times, not plus, times M is 0.2068 times L is 0.892, and this is power 3, divided by T is 0.45, and this is squared. So I'm now pressing my calculator. That is 1.48 exponent 5, and it is squared, times 0.2068 times 0.892 squared, divided by, oh, it was cubed, so I will say times 0.892 because it was cubed. Then divide by 0.45 squared. So this is 1.588. 1.588 times 10 power 10. Yes, times 10 power 10. That is E. Then I want the uncertainty, because we want even the uncertainty. Because they are in percentages, I will just sum up. Percentage in E is going to be twice percentage in K because of the power on K, plus percentage in M, plus 3 percentage in L because of the power on L, plus twice percentage in T because of the power on T. So this is going to be 2 times 1.5 for K, plus M is 0.1 plus 3 times L, which is 0.2, plus T, which is 2 times 2. And this gives me, that is 3.1.7, that is 7.7. So percentage is 7.7, then absolute uncertainty in E is equal to 7.7 divided by 100 times the value of E, which is 1.588 times 10 power 10, which is equal to, so that one times 7.7 divided by 100. So this is going to be a 1, 2, 3, 4, 5, 6, 7, 8, 9, 1.22 times 10 power 9. I want to write it as a power of 10, which will be 0.122 times 10 power 10. To write it one significant figure, it will be 0.1 times 10 power 10. That is one decimal place. So I'll write the answer as 1.6 to one decimal place plus or minus 0.1, and the whole of this is times 10 power 10. Let part 1 stop there for now. Let's meet in part 2, and I think part 2 will be the last. Thank you and bye bye.